Okay, 18.4 now starts getting the discussion of some more physical properties of carbonyl compounds, such as boiling points. So you can see the difference here between butane, which has van der Waals forces, has a boiling point of 0. You then get to the ethyl methyl ether, which is you now have dipole forces. And then you get to the carbonyl compounds. Carbonyl compounds are a little bit higher because they're much more polarized. You get a much more polarized bond. You get a much stronger bond. When you kind of form a dipole bond, the dipoles are a little bit stronger because you have a much more positive, partial positive charge on the carbon than you do with partial positive on these carbons because of the pi bond and the sp2 character. So that's why you get a big jump, big drastic jump in boiling points. Also, ketones are usually a little bit higher in the boiling points. And just to kind of compare with an alcohol, obviously with hydrogen bonding, it's almost twice as higher than the carbonyl compounds. Okay, so ketones and aldehydes are more polar, so they have higher boiling points than comparable alkanes or ethers. They cannot hydrogen bond with each other, so the boiling points are lower than the alcohol. But you can actually hydrogen bond this to, if you have a hydrogen. A lot of acetone, for example, has a lot of water in it. These compounds are what's called hygroscopic. They're hygroscopic, which means they pull water out of the atmosphere. They attract water pretty well. So they are notorious for that happening. And here's kind of to show you an example. The solubility of ketones and aldehydes. They, some of the smaller ones like acetone, formaldehyde, a lot of these aldehydes and types of ketones are soluble in water and in alcohols because of the fact that you can form the pretty good hydrogen bond with them. So they are a good solvent for alcohols. So if you're doing a reaction in alcohol, you can use aldehyde as a solvent or a ketone as a solvent. The lone pairs in the carbonyl can accept hydrogens for a hydrogen bond. And like I said, acetone and acetaldehyde or formaldehyde are soluble in water. All right. What's interesting is that some aldehydes and ketones actually form these type of molecules. All right. What happens, it's kind of interesting, is if you have your carbonyl and another carbonyl, what happens is this attacks this to open that up to give you a plus charge, an oxygen, a carbon, an O minus. This attacks another one like that to give you O minus with the plus there, and then that attacks over there to eventually give you some sort of a, it's what's called a trioxone. And when it's really, really dry, when you have all of the water out, that's kind of what aldehydes and ketones exist in these type of molecules. A little bit less in these kind of, in a polymer, they actually like to close up on themselves. But if you really dry this out, you really get the water out, they actually exist in these type of six-membered ring molecules. It's kind of interesting. This is just formaldehyde, just showing an example of formaldehyde. It's a gas at room temperature. So usually it's in a 40% solution. So if you do get a bottle of formaldehyde, it's not really formaldehyde. It's called a formalin, which is a hydrated form of formaldehyde. Okay, the trioxane is the cyclical trimer. And when it's heated, it generates formaldehyde because you put enough energy to drive off the water so that it re-collapses back into the aldehyde. All right, I think this slide is self-explanatory. Some industrial importance of aldehydes and ketones, really not a lot of excitement. Acetone and MEK are commercial solvents. They're used quite a bit in solvents. Formaldehyde is used as polymers to kind of make plastics. Like the Bakelite is like a ceramic type of a material that they put on pots and pans. Also, a lot of flavors and additives in food, but a lot of smells, a lot of compounds from our natural environment actually exist as a ketone or aldehydes. Here are just like some of them. A butyraldehyde is the smell in butter. Like butter has that like a distinct smell to it. Or if you get popcorn at the movie theater, You know, there's like that majorly, like that butter smell. Like as soon as you walk into the movie theater, well, this is what you're smelling. Okay, so next time you go to a movie theater, impress whoever you're with. Like, that is a butyraldehyde, by the way. Okay, you'll sound very intelligent. Vanillin, which is the main component of vanilla. There's an aldehyde right here. Which obviously is in food and perfumes and hand lotions. Pistachio, acetophenone, kind of has a pistachio or a nutty smell to it. Cinnamaldehyde is cinnamon. Camphor, we did a lab where we made camphor. Obviously, it's pretty pungent smell. This is kind of a really cool, complicated structure. It has two, actually that's an ester, but here's your ketone. Carvone, there's two forms. There's one that smells like spearmint. The other one smells like rye bread. It's the smell in rye. It's that rye smell to it. I guess this is the smell of musk. So there we go, just some examples. All right, we know this. Major review. A lot of this stuff is review. Grignards are added to ketones and aldehydes. That's the major reaction that you can do with a Grignard to form alcohols. And then obviously you can oxidize the alcohol with ketones. We'll talk about that in a different slide. But that's a review. Here you go. Here's oxidation. With PCC, we learn as a mild oxidizing agent. Also, we learned SWERN and the desmartin-pyridinane. I don't remember if we talked about that, but that's another reaction, mild reaction, where you can stop at the aldehyde. If you take a primary alcohol, you can stop at the aldehyde. Okay. Ozonolysis. We talked about ozonolysis. You take a double bond. If you have an R group on one side, you get the aldehyde. If you have two R groups, you get a ketone, and basically it just splits that bond in half, and it makes your ketone and your aldehyde. All right, so it's a double bond oxidation. Friedel-Crafts acylation, we just talked about this. You take an acid chloride. This is the acid chloride functional group, plus aluminum chloride and water, and you can go ahead and make a ketone. Or if you have an H here, we didn't talk about it, doesn't show it, but if you have an H right here, H, you can make the benzaldehyde. All right, this was an old reaction from last semester. Take a triple bond plus mercury and water, you form this enal. This is called an enal, where you have a double bond attached to the alcohol. This is not stable. Okay, what happens is this pops down, and then this pops onto the carbon, which this hydrogen eventually ends up over there. Okay, to give you the carbonyl compound. Okay, you also get the you always get the Merkavnikov. So if this is your starting material, your ketone is going on that carbon, the more substituted, because this only has a hydrogen. Now you can do the anti-Merkavnikov and make the aldehyde by doing the boron reaction, which we've talked about. It puts the OH on the least substituted, which then is the enol, and it forms the aldehyde. Okay, so these are kind of problems. I'm going to let you do these on your own. It just kind of shows you, how would you synthesize these compounds. It kind of has a red line showing you how would you make this bond and synthesize this compound. So I will let you do this on your own time. Okay, 18.8 is synthesis of ketones from carboxylic acid. So if you have a carboxylic acid, can you turn it into a ketone? And the answer is yes, you can. You can take an organolithium compound. Okay, you actually need to take two equivalents. Try to think, why are you using two equivalents? Why not just one equivalent? All right, well, the first equivalent, this is a carboxylic acid. Remember, carboxylic acid, in the presence of a very strong base, the first equivalent is going to pluck off that base and form this O- with the lithium. The second equivalent now is going to come in and attack on your carbonyl, just as we have here. So first equivalent quenches itself by plucking off a hydrogen. The second equivalent comes in and forms your compound. You add acid, you form what's called a hydrate, which we're going to talk about soon, and then the hydrate actually breaks down into the ketone. Okay, so this is where you can take organometallics. I don't think they work well with Grignards. You got to use an organolithium to form the diion. I don't think Grignards work very well with diions. All right, from nitrile, same thing. You can take a Grignard, add it to a nitrile, all right, form this imine salt. Remember, an imine, we're going to look at this again in this chapter. An imine is a carbon with a double bond nitrogen. That's called imine. Plus, when you add acid and water, it breaks this off to form the ketone. All right, so a Grignard organolithium reagent can attack a carbon on the nitrile, and the imine is hydrolyzed to the ketone. This is a very special reducing agent called dibal. Dibal. It's very common. It stands for diisobutyl aluminum hydride. Dibal H, I guess, if you want to call it dibal H. And it's a kind of a mild reducing agent. It doesn't really reduce carbonyls. It reduces other pi bonded heteroatoms. Okay, other pi bonded heteroatoms. It really does not do anything to carbonyls. Okay, so for example, dibal plus aldehydes really won't do much. But if you take a dibal and react it with a nitrile, you can add a hydride to it. So the hydride from here is going to the hydrogen. Okay, so the hydride is going to the carbon, kicks up to form this compound, and then acid and water, you form your imine again, which breaks down to the aldehyde. Okay, here again, here you have a double bond. It doesn't do anything to the double bond, but it reduces your cyano group, or the nitrile group. All right, aldehydes to acids, same thing. This isn't dibal, but this is also just as mild of a reducing agent. Acid chlorides are very reactive, so you don't really need that really reactive of a reducing agent. So using the lithium triterbutoxyaluminum hydride is good enough. Okay, mild reducing agent that reacts faster with acid chlorides than with aldehydes. So yeah, so the thing is, interesting thing is that this will not react with the aldehyde. I mean, we've seen reducing agents react with aldehyde. Well, these only reduce with really reactive carbonyls, but they do not do anything to aldehydes. If I were to use LAH in this case, not only would it reduce my acid chloride, but then it starts reducing my product. So if I want to go all the way down to the alcohol, then sure, I can add LAH and just reduce the whole thing. But if I want to stop at the aldehyde, here's the first time we're stopping at the aldehyde, is with these special type of reducing agents. Okay, this is a Gilman reagent. This is not a Grignard. It's like a Grignard, but it's much more mild. All right, it will just add, it will replace your chloride. Okay, so the R group here comes in and basically kicks out your chlorine. That's it. If I had a Grignard here, not only would it react with this, but then it would start reacting with my ketone. Okay, so that's why I didn't mean to scrape out ketone. I meant to underline this, but it'll start reacting with my ketone afterwards, which is something we don't want to happen. Okay, so that's why these dialkyl cuprates transfer one alkyl group and it won't keep adding to it. Okay, we're going to stop here, and the next video we'll talk about 18.11.